Welcome to another interview on the Zero to ASIC YouTube channel. Today, I'm really happy to be joined by Diego, who also was on the first Google Skywater Efabless shuttle. And one thing that's I'm really interested to find out more about is that Diego's done some analog designs, and everyone that I've spoken to so far has done digital ones. So Diego, maybe you could just introduce yourself and tell us a little bit about your background.
Yeah, sure. Well, my name is Diego. I'm from Argentina. I'm 27 years old, and I'm an electronical engineer. And currently, I'm doing a master's in analogic design of integrated circuits, and I'm working as well at a company doing some analog design. So meanwhile, I study. I do some little jobs. And yeah, basically, we have this opportunity to join the open source tape out of Caravel. And I had we have my team and I, we had an old design of an opamp in the 130 nanometers technology. And we wanted to give it a shot to try this new technology that we didn't see before. And also the whole design in an open source tools is something new for us. So it was a good experience.
So, have you done the op-amp? Have you? I think I saw that you'd also contributed to somebody else's shuttle.
Yes, we have in our chip we have 7 opamps, operational amplifiers. Those are 2 models, so we have 3 versions of one model and 4 versions of another model. We also have a ring oscillator and a PLL. The PLL is a contribution of another engineer that was doing as well Caravel run. So we also integrate his design to test it.
Okay. Is their name Lakshmi?
Yeah, Lakshmi.
Okay,
Exactly.
yeah, I've asked them for an interview as well, so hopefully I can talk to them about that as part of their design.
Exactly.
So maybe you can tell us a little bit about how the analog process differs from the digital process. So,
okay,
like my experience has only been from the digital. So I write some HDL, some Verilog, I put that into OpenLane, and then if everything goes well, it just ends up with the GDS2 files, and I get my digital gates all connected up into a block, and I send that to the factory, and ching, it's done. I mean, it's obviously not quite that easy, especially the first shuttle run. But do you have standard cells for analog? How does it work?
No. Well, it's quite different, actually. For example, I didn't use OpenLane at all. I used xschem and ngSpice to simulate at a schematic level, and then draw the layout by hand.
Did you use Magic to do that, or do you?
Yeah.
Okay.
I use Magic for that. If you let me, I can show you a quick slide that I have for
the interested in pictures
for this flow design. This is an old presentation that I have for another thing, but here I can explain you all the design flow for an analogic design of an integrated circuit. So we begin with the design specifications. In our case, for an op-amp, we have the gain that we want, the bandwidth that we want, the phase margin that we want, or the noise level, and other specifications. Once we agreed on the specifications, we do a schematic design and simulation at a schematic level. With in this case, we use xschem for the schematic design and ngSpice for the simulations. Once we are good with the results, we move to the layout design. Here we don't have any standard cells, as you say, so we draw the transistors one by one, not one by one, because in Magic you can draw one transistor and say, well, this transistor will have this length, this width, and it will be formed by, I don't know, maybe 10 transistors or more, and you have the whole package draw at once. Once the layout is done, we run some verifications. These are DRC and LVS verifications to check that the schematic and layout are the same. And if everything is okay, we run a parasitic extraction to get mainly resistance and mainly parasitic resistance and capacities that are around, and we simulate again with this new netlist with all the parasitics. And if we have an error that maybe we don't match one specification, we have to come back to the schematic design and change something until we have the specification that we want in the parasitic extraction. Once all the simulations are okay, then our design is done and we move to the tape out. That's something that, in this case, Skywater will do, that they will manufacture the chip. And once we get the chip, we do some testing to see if everything is working correctly.
Very convenient slide you've got there.
Yeah, it's another one.
So let me just ask a quick question, because
Yeah.
when I was learning Magic, as if I've now learnt it, but when I first started learning Magic, I was working on drawing an inverter, so just like a standard digital cell.
Yes, I saw your video to learn Magic.
Okay, I'm glad that was helpful. Well, I hope it was helpful.
Yeah, it was very helpful.
And one thing so when I did it before I had access to the Skywater 130 library, I just drew it at kind of like a random scale, and then I extracted, and then I was simulating. But when I switched to using the Sky 130 PDK, I found that I had to draw the transistors just the right size. Otherwise, when I did an extraction, it didn't work properly.
Yep.
So how do you get around that with the analog side? Do you have to follow the same rules? Do you have to draw like transistors a certain size, or do you have more flexibility?
Well, I have to respect the transistor size that I set on the schematic design. So when I run the LVS verification, they will match. If not, I have two different transistor sizes, and that's an error. The layout, it does not reflect the schematic.
Okay, so in your schematic, you might say this transistor needs to be a higher current one, so it needs a bigger
exactly. For example,
diffusion zone or whatever.
For example, let me show you. I have here my opamp schematic.
Oh yeah, great. Maybe you can just talk us very briefly through how it works.
Okay, so first of all, I can show you the specifications. I'm sorry, it's in Spanish. I didn't have time to translate it, but
that's fine. We know that the language of electronic engineering seems to get converted into English everywhere in the world.
Yeah, but it's almost the same as English here.
Gain product bandwidth.
Yeah.
Just reverse the words.
Exactly. So our specifications mainly is, it's another slide, but the idea is to use not 5 volt for VDD, but 1.8 volts. The reference current is 100 microamps, and we try to consume the lowest power possible. We have some specification for an open loop design and for a closed loop design. For an open loop design, we aim to have a 52 dB DC gain and gain bandwidth product of for at least 40 megahertz and a phase margin of 60 degrees. And for the closed loop design, we look for a DC gain of at least 20 dB. The gain bandwidth product for 40 megahertz as well. And for example, the open noise, well, this specification, I didn't follow it, but the common mode tension, it should be the half of the VDD. And we also consider different corner situation of the transistor manufacturing. So we have to test it in if the transistor come in a typical version, or a fast, slow, or the diagonals, we say fast and slow, or slow and fast.
So just a quick clarification here, because this isn't something that I'm particularly familiar with either. But this is when you're making a big wafer in the factory, the transistors made at one part of the wafer may have a different performance that somewhere else in the wafer. Is that correct?
Exactly.
So you have these different regions.
Exactly.
And those are part of the process design kit that the factory tells you this is how they may well differ.
Exactly.
So you need to make sure your design is going to work if it's on the corner or if it's in the center or wherever.
Yeah, it's not a physical location. I'm not sure if it's just something physical on the wafer, but maybe one transistor next to another, it might change a little bit how it works. So you have to test. It is good to test that your design will work in every possible combination of the functionality of the transistor. So in this op-amp design, I tested for all the possible corners. That's how it's called.
Okay, but they may be like corners
transistor.
of a graph rather than corners of a wafer.
Yeah, exactly.
Okay.
So our first step after we have our designs, after we have our specification, we design our op-amp. In this case, we use a Miller op-amp. It is called a Miller op-amp because we have this Miller net here. And what we do is to set the sizes of the transistor. At the first attempt, what we do is to have everything polarized in a good way. So our transistors are working in the saturation region and not in the triode region. Once we finish with the first polarization, to make it easier, we draw a symbol of this schematic. So I generate a symbol here for my op-amp, and then I create my open loop test bench at the beginning. Is this one? I have the
and this program is called xschem, right?
Yeah, exactly. It's xschem from Stefan Schippers. He also helped me a lot into getting used to the new tool.
Okay, so before this, you were using closed source paid for tools.
Yeah, I was using Cadence and Synopsys.
Okay.
It's not that different from Cadence xschem. It's quite easy to use if you are used to Cadence.
Okay.
So once we have our test bench, we have to give some SPICE directives that I have here in the simulation file. I specify parameters. Here is where I specify the library that I'm using.
Okay, so that's something that I've also touched on when I was doing the simulation of the inverter, because you have to pull in the reference from the PDK, so you've got the simulation there.
Exactly, and here is where I say which corner do I want to test. So if I write TT, I'm watching a typical configuration. if I write FF is fast, fast, or SF, for example, is slow and fast. So let's leave it in TT. And here I specify to save some parameters of the transistor, like the drain current, the threshold voltage, the gate source voltage, and so on. And here I specify the simulations that I'm running. Here I'm running mainly an AC simulation. After that, I just generate the netlist and simulate, and I get the results. And I do the same for the closed loop design, the closed loop bench to achieve all the specifications that I want. So here I have the body diagram. It's not quite easy to read, but here you can see my gain bandwidth in typical configuration is 85 megahertz, so I'm way above 40 megahertz, and my DC gain is 58 dB. So I fulfill my specifications, and also the phase margin is 58 degrees, so I'm fine. And I have to repeat this for all the corners.
Okay, to check that you meet your specifications.
Exactly. After that, I do the same for the closed loop design. That's it. The closed loop design is actually, I think it's actually the most important one, or the main one, because it's the way I will use the opamp later once I have it delivered to Argentina, right?
Okay, so it's using the same design that you have, but your test bench is in closed loop instead of open.
Exactly. So you can see I don't have the 1 gigahertz resistor. It is in a closed loop configuration. And here I can run the simulation again with the same configuration and see if I fulfill the specifications.
For closed loop. Cool. So maybe you could show us how you drew this out in Magic then.
Yep.
It's like the next step in that.
Well, once we finish this, we move to Magic and draw this design. Here you can see, well, what we do to draw this is, for example, if I want to place a new device, I go to Devices, select an NMOS, and here I can specify the width, the length, the number of fingers that I have.
Is fingers like the number of transistors that you have within a big transistor? So if you need bigger drive strength,
yeah, exactly. Yeah, for example, let me show you here.
You have to remember, I'm a complete analog beginner.
Yeah, no problem. I'm also not an expert. I'm still learning.
Maybe I'll do it on my next tape out.
Here, for example, this transistor, that is the current copy transistor. I have 15 transistors of 3 micrometers by 300 nanometers. But I have 15 transistors. So okay, instead of having 15 transistors separately and connecting them with a metal or poly or any layer, I just overlap the drains and source of the next transistor, and they are connected. And that's a finger.
Okay, and I see on the outside, on the output, you've got 150. So those are presumably the really big shapes.
Here you have 150 transistors. Here you have the 15 transistors.
Could you just zoom in a little bit on that?
There, it's fine.
Yeah, that's good then.
So here you have 15 transistors. 1, 2, 3. Yeah, 15 transistors. And these are fingers, because instead of having 15 separated transistors and connecting them, I am overlapping drain and source from the transistor. So that's a finger.
Okay.
So I do the same for the rest of the transistor. Here I have the M8. So just a quick look for you to remember. This is M8. M5, M7, and this is the differential pair is M1, M2, the load, and the output amplifier. Yes. In the layout, that would be this is M8, this is M5.
Where you're showing the cursor is not matching up with there we go, now it's updated. Show us again.
This is M5. You have 30 transistors.
Okay. The screen takes a few seconds to update, so.
Yeah, that's true. No problem.
Yeah, okay, I see those.
This big one is the 150 transistor. That is M7.
Okay.
This
now
two.
The screen just updated. So we see that now. Okay, now it's zoomed out. Oh, that huge block there. What's that?
This huge block. This is the differential pair. So you have one transistor here, and the other one here.
Okay.
And down there you have the loads of the differential pair.
Just hold on a minute. There we go.
Yeah.
Now it's updated.
Perfect.
Yeah.
And one last zoom. And this other big transistor here.
Just wait a minute. There we go.
Yeah. This last big transistor is the output amplifier.
Okay. And what are the 6 kind of blocks with this diagonal lines through them?
This is a capacitor.
Okay.
This is the Miller capacitor here.
Okay.
Let me show you the schematic. This capacitor.
Okay, so that's how big is that capacitor in farads? 3
picofarads.
Picofarads. Okay, so it's quite a big area you need for even a small transistor, for a small capacitor.
Yep. Yeah. And actually, it's a quite small design, I think. For when I show you I will show you the wrapper later, and you will see that the op-amp actually is quite small.
Yeah. Okay, so you've drawn this out in Magic, and then you can do the extraction with the parasitics. So then you can rerun your simulation and check that it matches the simulation you get with xschem. And then what's the next step?
Once all the simulations are okay, then it's the integration into Caravel to send it to the Skywater and Efabless webpage.
Okay. And you don't actually use OpenLane to do that. You just need to use the make command at the end that merges the user project wrapper into Caravel.
Exactly. What I did was, after I finished my opamp layout, I integrated in the user project wrapper. I will show you right now. User project wrapper. User project wrapper. Here you can see it. There is this, for example, this opamp. Just
so
this
really
opamp.
Empty. Okay.
Yeah. That opamp is the one that I show you.
Okay.
Just
and then you just wired it all up by hand, just drew the lines in Magic.
Exactly. Yeah, I did all these lines that you see are power grids.
Yeah, it looks totally different to mine because when I ran OpenLane, it generated the power delivery network of like 4 different supplies in a very fine mesh. So it was completely covered.
I have to draw that by hand, so
you didn't bother.
all these lines that you see here are all the power is the power grid that I draw by hand.
Okay,
to
but
make
you
sure
don't actually need that much, do you? Because you know where your modules are going.
Yeah, exactly. But it's something that I did to make sure that all the op-amps get the same amount of VDD. And just in case that maybe there is one connection that is not quite good, I have multiple connections to make sure that the op-amps will be correctly supplied.
One question for you. With the digital flow with OpenLane, you get a lot of decoupling capacitors put everywhere for you, like sprinkled throughout the entire design. Do you need to decouple your op-amp designs by deliberately putting decoupling capacitors in, or?
No.
Okay.
I didn't do that. What I have to do is that because I need to use analog signals into Caravel. I mean, the connection between the Caravel path and the user project wrapper needs to be an analog path, not a digital one. I have to change some routing in the Caravel design to make sure that I can use the analog path.
Okay. I thought those analog pins were exposed as part of the user project wrapper.
Yeah, but the ones that you get exposed are, yeah. I mean, yes, I have. If you see here, I connected to the analog pin in the wrapper, but this analog pin is connected to a path with an ESD. It has a big impedance, and there is also a pin available that has no impedance, and we wanted to use that one.
Okay.
That's the routing we did.
Here's another question that's maybe about the difference between the digital and the analog is all my designs, they're not going to do anything until the RISC-V chip, Pico RV32, boots up, loads its firmware, runs a program that sets the IOs correctly, and then my design should run. Will your design just run without any external flash because there's no configuration needed?
In the case of the opamps, yes.
Okay.
They don't need configuration from the Pico microprocessor, but in the case of the ring oscillator and the PLL, I have to enable the outputs because they are digital, and I have to, for the PLL, I have to enable the clock so it can run.
Okay. Cool. Okay, I've got one more question for you because we're kind of running out of time a little bit here. So this has all been sent off now, and we're going to get it back in a few months, and I'm sure it's all going to work perfectly.
Hopefully.
But how will you actually qualify the design? Can you talk us briefly through how you'll do the testing?
Well, with the Caravel shipping, we have also these test boards where we can put the chip and we run. I'm not quite sure yet about the test that I will run, but I have to check that I have the gain that I want, the bandwidth that I want, the noise that I want, and all the stuff.
So will you use a tool like a curve tracer to measure the parameters, or will you make measurements with a multimeter or a scope or a signal generator? How will you do it?
Yeah, with the scope mainly.
Okay.
With the scope and wave generator. Yeah, like a typical electronic chip, test circuit. Yeah.
Cool. Okay. That was really interesting to hear how the whole flow goes on the analog side.
It's a little bit different from the digital one.
Yeah. Is there anything that you want to share with us? Any projects that you're working on, or anything that you want to let people know about?
Well, this experience with Caravel was quite good. We are currently doing some new designs, especially for my master thesis. I'm working on PLL, so I'm studying them and making some designs to add them in a future run of Caravel. So maybe we can use the tape out again in a future opportunity.
We'll do another interview once you've done your testing.
Well, I have no problem.
Great. Okay. Well, Diego, thanks so much for your time. It's been really interesting talking to you.
Please.
And
yeah, perfect. Thank you, Matt. Bye-bye.
Bye-bye.